Hello, and welcome to the world of aviation. Today's YouTube lecture is on emerging surveillance systems. We take a look at automatic dependent surveillance and its impact on air traffic control. Now, this is not an academic lesson, but rather an informative talk, and the views expressed in this lecture are subject to change and improvement. Allow me to extend a very warm welcome to a very special group of people, the young aviators. Before going into the discussion of automatic dependent surveillance, let us take a look at the development of surveillance as a tool of controlling aircraft. Initially, the industry relied purely on procedural control. In this method, aircraft are separated using laid-down procedures. This method is still used in the absence of radar or other forms of surveillance. Now, in the early 50s, to be specific, January 1952, according to records, and after the Second World War, radio detection and ranging, commonly known as radar, was adopted as a means of surveillance for aircraft by the aviation industry. This is a technology which was borrowed from the military. Now, this is a surveillance radar system which uses reflected radio signals. In this separation method, the radar antenna emits a pulse of radio wave, and upon reaching an aircraft, the wave is reflected. The reflected energy is received by the radar antenna and is used to plot the position of the aircraft on the controller's display. It is also used to display more information for the controller depending on the mode of operation. It could be mode A, mode C, or mode S. Therefore, we could say with the primary radar, the controller is able to know the position of the aircraft independent of the aircraft or without the assistance of the aircraft. Now, the need to be able to identify aircraft more easily and reliably, especially in a crowded airspace, led to the development of what we now know as the secondary surveillance radar, or commonly known as SSR. It relies on a piece of equipment on board an aircraft known as the transponder. The transponder is a radio receiver and transmitter pair which receives on a frequency of 1030 MHz and transmits on 1090 MHz. So the radar antenna transmits a pulse which is received by the onboard transponder. The transponder sends back a reply containing information like the aircraft identification, selected level, and many others. In other words, the ground equipment cooperates with the onboard equipment to determine the current position of the aircraft. It should be recalled that the main problem with the traditional surveillance systems which are the primary secondary radar and the secondary radar, is a problem of line of sight. Radar has a limitation of coverage. So the aviation industry anticipated a system that is capable of extending surveillance service beyond the line of sight to oceanic airspace, remote land areas, and other areas where radar coverage is not available. To overcome this problem, the aviation industry turned to automatic dependent surveillance. In this system, the system is totally dependent on the aircraft transmitting or broadcasting information to its surroundings. What is ADS? It can be defined or described as a method of surveillance that relies on downlink reports from an aircraft's avionics that occur automatically whenever specific events occur or specific time intervals are reached. ADS does not require an independent surveillance source, such as a radar antenna, to operate. Due to this capability, ADS can provide accurate surveillance reports in remote and oceanic areas that, for a variety of reasons, will never be inside radar coverage. The ADS reports are converted by data link equipped ground stations into an ADS track and presented on the controller's air situation display to provide enhanced situational awareness and the potential for reduced separation standards. There are two prominent implementations of ADS that are inherently different. The first one is ADS broadcast or ADS-B, and the second, ADS contract, also known as ADS-C. What is ADS-B, or automatic dependent surveillance broadcast? It is a surveillance application broadcasting parameters via broadcast mode data link, which can be VDL or VSAT, and at specified intervals for utilization by any air and/or ground users requiring it. These can be airlines, air traffic controllers, search and rescue, or any other aircraft in the vicinity. The aircraft originating the broadcast normally has no knowledge of which systems are receiving the broadcast. Any air or ground-based user may choose to receive and process this information. The aircraft broadcasts information such as position, identity, speed, latitude, longitude, track, and in air traffic control, it provides information to tower, ground operations, apron, and runway. And for the airlines, it can provide information to the airline operating center. An ADS-B equipped aircraft determines its position by a satellite navigation system like the GPS or other sensors and periodically broadcasts its position and other related data, enabling it to be tracked or discovered by users like the air traffic control on the ground, aircrafts within the vicinity, or even satellite. Unlike the SSR or secondary surveillance radar, ADS-B does not require an interrogation signal from the ground or from any other aircraft to activate its transmission. It automatically transmits information without any external assistance. It is projected that ADS-B will progressively replace radar and become the preferred means of air traffic management on surface, terminal, approach, and route, and more importantly, oceanic and remote areas via satellite ADS-B. So what benefits are we looking at when ADS-B is finally in place? ADS-B services will enable a number of operational benefits to be realized, especially in oceanic and remote areas. These benefits include reduced position report errors, eliminate the need for pilot voice position reporting, coverage in non-radar airspace, reduced separation minima, hence increasing efficiency, more direct flight paths, more accurate data, environmental friendly, there'll be less pollution, and eventually cost saving. Now, let us discuss automatic dependent surveillance contract. So what is automatic dependent surveillance contract, also known as ADS-C? ADS-C is a surveillance point-to-point application which is based on an ADS agreement. It is a means by which the terms of an ADS-C agreement will be exchanged between the ground system and the aircraft via data link, which can be either VHF or satellite, specifying under what conditions ADS-C reports would be initiated and what data would be contained in the reports. Now, all contracts, with the exception of the emergency ones, are initiated and managed by the ground system. There are basically three basic contract types: the periodic, the event contract, and the demand contract. The periodic contract specifies the reporting rate at which the avionics is required to assemble and downlink the requested information to the ground system. Only one periodic contract can be established between a ground system and a specified aircraft at any one time. Once a periodic contract is established, it remains in place until it is cancelled or replaced by another periodic contract. Controllers in some systems have the ability to alter the periodic reporting rate to cater for situations such as traffic density, where a higher or lower reporting rate is required. The event contract specifies a requirement for a downlink ADS report to be assembled and sent whenever specified events occur. Multiple event contracts can be established between a ground system and a specified aircraft. Now, the event contracts which are available are the vertical rate change event, the lateral deviation event, the altitude range change event, and the waypoint change event. The vertical rate change event is triggered when the aircraft's vertical rate is greater or less than the parameter defined in the contract request. The lateral deviation event is triggered when the aircraft's actual position exceeds a lateral distance parameter from the aircraft's expected position on the active flight management system plan, as defined in the contract request. The altitude range change event is triggered when the aircraft's altitude exceeds the altitude ceiling or floor defined in the contract request. Each of the events or event contracts discussed above has a life of only one event. When the specified event has occurred, the particular event contract must be reinitiated by the ground system. The waypoint change event is triggered if the next or the next plus one waypoint is different from what had been intended. This change normally occurs due to normal waypoint sequencing by the flight management system of the aircraft. The next or next plus one waypoint can be either an ATS waypoint or a pilot inserted waypoint. The demand contract is a one-off request made by a controller for an ADS report containing only the basic ADS group. A situation where a demand contract report is useful is when an ADS aircraft is climbing or descending. The ADS level displayed for the flight data record does not update dynamically. That is to say, unlike a Mod C level readout, that is radar, the ADS level displays the last level information reported and does not change until a new report is received. Now let us look at some of the information that we expect to see in these reports. The first one we want to look at is the ADS groups. The basic group is sent with every downlink ADS report, and it contains the current latitude, longitude, altitude, a timestamp, and a figure of merit. The figure of merit ranges from 0, the worst case, to 7, the best case. The figure of merit will degrade over time if a navigational update does not occur. For example, if the GPS input fails. The figure of merit value is generally not presented to the controller directly, but some ground systems use the figure of merit when deciding whether to paint the ADS track as a high quality or low quality ADS symbol. That is, it may be amber, red, or green. Now, a number of other on-request data groups are also available for inclusion in the ADS report should the controller want, in addition to the basic group. These are flight identification group. The controller may wish to know the flight. Earth reference group, the air reference group, the airframe identification group. Again, the controller may wish to know the fuselage of the aircraft. Meteorological group, the predicted route group, the fixed projected intent group, and finally the intermediate projected intent group. Now, let us have a look at an example of an ADS contract. This particular example represents the flight path of an aircraft. The drawing is simply for explaining the ADS-C and does not represent the flight management system of the aircraft. So the aircraft is flying from point A to point F. Point A represents the current position at 060 hours. Point B represents top of descent, which is a zero waypoint inserted by the aircraft's flight information system. Point C is an ATS reporting point, CACU, on the flight path. The flight plan indicates that the pilot intends to change speed and the request for descent at this particular waypoint. Point D has been inserted by the pilot in the flight management system to trigger a report to the airline's operational control center. Point E is another ATS reporting point, CARDO. At this waypoint, no changes in speed or altitude are planned to occur. Point F therefore represents the aircraft's fixed projected intent group position requested by the ground system for 60 minutes ahead of the current position A. From the flight path, points A and F will be reported as a fixed projected intent point. Point B and point C will be reported in the intermediate intent report, as there is an intention to reach top of descent at point B, and there is an intent to change speed and altitude at ATS waypoint C. At point D, no report will be sent to air traffic control, as this point was inserted by the pilot to trigger a report to the air operator's control center. Also, no report will be sent to the air traffic control at point E, since there is no intention for any change at this waypoint. Therefore, what we are saying here is that in this report, the fixed projected intent will be reflected at points A and F, and intermediate intent or event contracts will be reflected at point B and C. Now, the benefits of ADS-C to air traffic management will include a reduced workload, reduced separation, reduced delays, enhanced safety, increased capacity, reduced flight operation cost, and reduced environmental pollution. For those of you who wish to learn more about ADS-C and ADS-B, I would recommend that you look at material by Keough and the Sky Library. So thank you for staying with me up to the end of this lecture, and I hope to see you again in the next lecture. Thank you and goodbye.